On December 11th, 2024, thousands of AI products stopped working at the same instant. Customer support bots went silent. Coding assistants stopped completing. Marketing tools, chat apps, internal co-pilots, all frozen for over 4 hours. Not because any of them had a bug, because they all made the same architectural decision. They called one provider's API directly, and that provider, OpenAI, pushed a new telemetry service that accidentally overwhelmed its own Kubernetes control plane and took the whole platform down. One vendor sneezed, and half the AI economy caught pneumonia. And here's the part that matters for this interview. Every one of those teams could have stayed up. Another model provider, Anthropic, Google, an open model on their own GPUs, was running fine that afternoon. The failure wasn't the outage. The failure was having no layer that could reroute the traffic. That layer has a name, and it's what this whole video is about. The AI gateway. Because the moment your product depends on a language model API, you have quietly outsourced 3 things you used to own: your reliability, your cost structure, and your safety boundary, to a company you don't control, that is rate-limited, priced per token, occasionally down, and speaks a different dialect from every competitor. The gateway is the single layer where you take all 3 back. Miss that framing, and you'll describe a proxy that forwards requests. Get it, and you'll design the control plane that every serious AI company is building right now. Frame it before you build, because put a gateway in front of the LLM is not a spec. Start by naming what an LLM call actually is, because the whole design falls out of it. It is a slow, non-deterministic, metered per token, rate-limited network request to a third party that can fail or disappear. Every requirement is a response to one of those properties. Functionally, the gateway is the single entry point for all LLM traffic. It exposes one unified API, routes each request to the right model, and returns a normalized response while transparently handling caching, retries, failover, rate limiting, and logging. Non-functionally, state them as properties. Low added latency, because it sits on the hot path in front of a call users are already waiting on, so it must add single-digit milliseconds, not tens. High availability, because it's now a single point of failure for all AI features, so it must be more available than any provider behind it. Cost control, because every request costs real money, so budgets, caps, and attribution are first class. And safety and auditability, because every request is logged, attributable to a tenant, and screenable for policy. The clarifying questions that signal seniority. How many providers and models must we support? And will that set churn? What's the traffic? Say tens of thousands of requests per second at peak across many teams. Is it interactive and latency critical, or batch and throughput critical? Multi-tenant across teams, or a single app? And what's the compliance posture? Regulated data, personal information, data residency. Then the one sentence that reframes the interview, say it early. An AI gateway is not a proxy, it's a control plane for AI traffic. Its job is to make an unreliable, expensive, non-deterministic external dependency behave like a reliable, budgeted, governed internal service. Before drawing boxes, defend why this is its own system, because the naive answer is, just call the OpenAI SDK from each service, and you need to kill that cleanly. Picture an organization with a dozen apps that each want to use 3 or 4 model providers. Without a gateway, that's an N by M problem. Every one of the N apps independently integrates every one of the M providers, its SDK, its auth, its retry logic, its rate limit handling, its cost tracking, its safety filters. Now multiply the pain. A provider ships a breaking API change, and you patch it in a dozen places. You want to add a cheaper new model, a dozen deployments. A provider key is leaked, you rotate it across a dozen codebases. One team writes a runaway loop, and no central budget stops it. Security wants to redact personal information on all prompts, and there's no single place to add it. These are all cross-cutting concerns: reliability, cost, security, observability, and the entire history of software says you don't scatter cross-cutting concerns across every caller. You factor them into one layer. That's exactly what an API gateway did for microservices, and the AI gateway is the same move for LLM traffic. Collapse N by M integrations into N apps talking to one gateway and one gateway talking to M providers. The gateway exists because reliability, cost, and safety are cross-cutting concerns, and the only sane place to implement a cross-cutting concern once is a shared choke point every request already flows through. Now the architecture, and the cleanest way to present it, is as a request lifecycle. The ordered pipeline every call runs through, because the order itself encodes the design. A request arrives and flows. 1. Authenticate and identify the caller, which app or tenant, via a virtual key. 2. Rate limit and budget check. Is this tenant within its request, token, and dollar limits? Reject early if not, before spending money. 3. Cache lookup, exact match first, then semantic. A hit returns instantly and skips the provider entirely, and this is where most of your savings live. 4. Route. Pick the model and provider for this request based on policy, cost, quality, latency, availability. 5. Call the provider with a timeout through retry and circuit breaker logic. 6. Normalize the response into the unified schema and stream it back if streaming. 7. Login meter. Record tokens, cost, latency, cache status, and tenant for observability and billing. 8. Populate the cache for next time. 2 structural points elevate this. First, split control plane from data plane. The data plane is this hot request path and must be lean and horizontally scalable. The control plane is where you configure routing rules, budgets, keys, and policies, and it must never sit on the hot path. Second, say this unprompted because it's the #1 real-world failure of a gateway. The gateway is now on the critical path of every AI request, so its own latency and availability dominate. It must add single-digit milliseconds, be stateless so you can scale it horizontally, and keep its shared state, cache, counters, config in fast external stores so no single instance is special. The gateway's power comes from being the choke point, and its danger comes from the same place. The first job of the gateway is the most mundane and the most quietly valuable. Give every app one API and hide the fact that providers disagree about everything. OpenAI, Anthropic, Google, and a dozen open models all expose similar capabilities through incompatible interfaces, different request schemas, different names for the same parameter, different ways to do system prompts, tool calling, JSON mode, and streaming, different error formats, different token accounting. If every app hard codes one provider's shape, switching providers means rewriting apps, which is exactly what kills your ability to fail over or cost optimize later. So the gateway exposes one canonical schema and translates in and out. The pragmatic detail worth naming: the industry has largely converged on the OpenAI-compatible API as the de facto standard. So most gateways speak OpenAI in, OpenAI out, and adapt every other provider to it, which is why you can point an app at a different model by changing one string. 2 subtleties that show depth. Normalization is lossy. Provider A supports a feature provider B doesn't, say a specific tool calling mode or a 2 million token context. So your unified schema is either a lowest common denominator or it needs graceful per capability fallbacks. And streaming makes translation harder. You're not transforming one response body, you're transforming a stream of chunks in real time in different per-provider formats without adding latency. The unified API is what turns which model into a runtime config decision instead of a code change, and everything valuable downstream, routing and failover especially, is only possible because the app no longer knows or cares which provider answered. Caching is where the gateway earns its budget. So we go deep. And the key insight up front is that there are 3 different caches operating at different layers, and strong candidates name all 3. The first is the simplest, exact match caching. Hash the fully resolved request, model prompt, parameters like temperature, and if you've seen that exact input before, return the stored response with 0 LLM calls. It's cheap, it's always correct, and for workloads with genuine repetition, the same FAQ, the same document summarized repeatedly, it's free money. Its limit is obvious. Natural language almost never repeats exactly, so on conversational traffic, the hit rate is low, and you must key carefully, because a temperature above 0 means the user wanted variety, and any per-user or time-sensitive content must be part of the key, or you'll serve stale or cross-user data. The second cache isn't yours at all. It's provider-side prompt or prefix, caching, and knowing it is a strong senior signal. It's a key-value cache trick. When a long prompt shares a prefix with a previous request, a big system prompt, a fixed instruction block, a document you keep asking about, the provider reuses the computed attention tensors for that prefix instead of recomputing them, and bills the cached prefix at a steep discount. The numbers are real. Anthropic charges roughly 10% of the base rate for cache reads, a 90% discount, while charging about 25% more for the initial write. OpenAI auto-caches prefixes over about 1,000 tokens. Gemini offers explicit caching around 90% off. The gateway's job is to structure prompts to exploit this, put the stable, shared content first so the prefix matches, and to know the trap. If you put anything volatile, a timestamp, a request ID, at the front of the prompt, you break the prefix match on every call and can end up paying the right premium with no discount, worse than not caching. Now the famous one, the semantic cache, and the idea that makes this a staff interview. Exact match misses everything that means the same thing in different words, so instead of hashing the text, you embed the question into a vector and search a store of previous query embeddings for a near neighbor by cosine similarity. If the closest cached query is within a similarity threshold, you return its stored answer, no LLM call. Production hit rates land between 30 and 70%. Published systems cut API calls by up to 68%, and roughly 31% of LLM queries are semantically similar to a previous one. So far, it sounds strictly better. It is not. An exact match cache can be stale, but it is never wrong. A semantic cache gives that guarantee away on purpose, and the price is a correctness and safety risk most teams never put a number on. It is the only optimization in your entire stack that can confidently serve the wrong answer to the wrong user in under a millisecond. It all hinges on that similarity threshold, and there is no correct value. Set it too loose, and you get false positive hits. What's the refund policy for orders over $100? Matches the cached answer for orders over 10. and you return a confidently worded, completely wrong answer, fast, with no LLM in the loop to catch it. Set it too tight, and your hit rate collapses. Then the scary one, cross-user leakage. If you cache, "What's my account balance?" keyed on the meaning of the question, the next user asking the same question gets the first user's balance, a data breach at cache speed. So any personalized or permissioned content must be partitioned by identity in the cache key, never shared across users. It's even adversarial, vulnerable to key collision attacks that craft a query to collide with a target's entry. Treat every semantic cache hit as a probabilistic bet that can be wrong, so scope it to low-stakes, non-personalized, high-repetition traffic, partition the key by identity, set TTLs, tune the threshold against a real error budget. And for high-stakes answers, either don't semantic cache at all or verify the hit before serving it. If caching is how you avoid calls, routing is how you make the calls you can't avoid cheaper and better. The naive design sends everything to one big model. The insight: most requests don't need your most expensive model. Summarize this in one line and prove this theorem should not cost the same. But a single model setup charges frontier prices for trivial work. So the gateway routes each request to the right model on a cost, quality, latency trade-off. Several strategies, simple to sophisticated. Rule routing. Explicit rules by app or task type. Classification tasks to a small cheap model. Legal drafting to a frontier model. Transparent but brittle as tasks multiply. Predictive routing. A tiny, fast classifier at the front door predicts how hard the query is and sends easy ones to a small model and hard ones to a big one. The root LLM line of work, which can cut cost dramatically while holding quality. Its trade-off: the router can misjudge and send a hard query to a weak model, so you tune the routing threshold against a quality budget. And cascading, the most elegant: try the cheap model first, run a quality estimation check on its answer, and escalate to the stronger model only when the cheap answer is judged inadequate. You pay for the big model only on the queries that actually need it, and research shows cascade plus routing beats either alone. Its cost is latency and complexity. A bad escalation means you paid twice and waited longer, so escalation only wins when a large fraction of traffic is genuinely easy. Routing also serves latency. Send to the fastest provider. Availability: avoid a degraded one. And capability: only some models do vision or long context. Routing is portfolio management for models. Match each query to the cheapest model that will answer it well, escalate only on demand, and treat which model as a live per-request decision the gateway owns. Back to the cold open, because reliability is the reason the gateway exists. Providers will fail, full outages, partial degradations, rate limit rejections, timeouts, and random errors. And at millions of requests a day, every provider fails, eventually, is a certainty, not a risk. The gateway is where you make provider failure. Stop being product failure. Layer the classic resilience patterns and name them precisely. Timeouts. Never wait forever on a hung generation. Bound every call. Retries with exponential backoff and jitter. For transient errors, 429s, 500s, timeouts. Retry a bounded number of times with growing, jittered gaps so you don't stampede a recovering provider. The subtlety most people miss: LLM calls are expensive and often streaming, so blind retries cost real money and can double charge, so retry only idempotent safe failures and never silently retry a call that already produced billable tokens. Circuit breakers: track each provider's health, and when its error rate crosses a threshold, trip the breaker. Stop sending traffic for a cooldown instead of hammering a service that's clearly down. then probe to see if it recovered. And the payoff pattern, the one that would have saved everyone in the cold open. Fallback chains, an ordered list of alternatives, OpenAI, then Anthropic, then a self-hosted open model on your own GPUs. When the primary trips, the gateway transparently reroutes to the next, and the app never knows, which is only possible because of the unified API. Name the honest trade-offs. Fallbacks assume the models are substitutable, but a prompt tuned for one may behave differently on another, so you accept degraded service over no service, and you should actually test the fallback path. The stat that lands by mid-2025, roughly 40% of production LLM teams ran multi-provider routing, up from 23% 10 months earlier. The December outage taught the whole industry this chapter. Now, the job that pays the gateway's rent in most orgs. Stop the bill from exploding. Two forces make LLM cost uniquely dangerous. First, you're bounded by the provider's rate limits, requests per minute, and tokens per minute. And if one team blows through the shared quota, everyone's requests start getting rejected, a self-inflicted outage. Second, cost scales with tokens, invisibly, a single buggy loop or a prompt that accidentally stuffs a huge document can burn thousands of dollars before the monthly bill reveals it. So the gateway enforces limits, and the senior insight is what you limit on. Rate limit on tokens, not just request count, because 10 requests per second is meaningless when one request can be 200,000 tokens and the next is 20. Layer the controls, per tenant quotas, so each team gets a bounded slice of the shared capacity. No noisy neighbor starving the rest. Hierarchical budgets, daily and monthly dollar caps per team, per app, per environment, so dev and CI can't spend prod's budget. And hard cost caps that reject requests when a budget is exhausted, which is why the budget check sits early in the life cycle. You reject before you spend. Pair it with spike protection and cost attribution so every dollar maps to a team. The trade-off, to state, hard caps protect the budget but can break a product mid-task if set carelessly, so distinguish soft alerts, warn at 80% from hard stops, reject at 100, and let critical paths degrade to a cheaper model rather than fail outright. LLM spend fails silently and fast, so meter in tokens and dollars, not requests. A gateway serving many teams or customers is a multi-tenant system, and that raises two problems juniors skip. First, key management and secret brokering. The real provider API keys, the ones that can spend unlimited money, must live in exactly one place. The gateway's secret store, never in the apps. Apps instead get virtual keys, per team tokens the gateway issues, and the gateway maps a virtual key to the real credential at call time. This is a big win on three axes. Security. A leaked virtual key is scoped and instantly revocable at the gateway without touching the real key or redeploying apps. Attribution. Every request is tied to a specific virtual key, so cost and audit are per tenant by construction. And control, you can attach each virtual key to its own budget, rate limit, model allow list, and routing policy. It's also the direct answer to a security question. Never put the provider key in the model's context or the app's client. Broker it. Second, tenant isolation and fairness. The same noisy neighbor problem as any shared platform. One tenant's spike or huge context must not degrade others. Defenses. Per tenant rate limits and budgets, fair queuing across tenants so one backlog doesn't drain the shared provider quota, and, for large or sensitive tenants, dedicated capacity or even dedicated provider accounts. And crucially for the cache, tie back to the semantic cache chapter. Cache and rate limit state must be partitioned by tenant, or you get cross-tenant cache leaks and one tenant consuming another's limit. The gateway brokers' secrets so real keys live in one revocable place, while apps hold scoped virtual keys, and it enforces per-tenant isolation, so a shared control plane never becomes a shared blast radius. Because every request flows through it, the gateway is the natural, and often the only, place to enforce organization-wide safety and compliance policy. This is the third of the 3 jobs from the cold open, and it hands directly to the AI security discipline. On the input side, detect and redact personal information before prompts leave your network for a third-party provider, because you may be contractually or legally barred from sending customer data to a given vendor, and scan for prompt injection and abuse on agentic traffic. On the output side, data loss prevention scanning to catch secrets, personal information, or policy-violating content before it returns to the user, plus content moderation. And across both, the gateway is the audit boundary, the single, enforced, logged checkpoint where policy is applied and recorded, which is exactly what compliance regimes and increasingly regulation like the EU AI Act want to see. State the honest limits. Guardrails at the gateway are a layer, not a wall. Injection scanners are probabilistic and bypassable. Redaction can miss, and putting a heavy safety model in line adds latency to the hot path. So you run cheap, fast checks inline and heavier analysis asynchronously. You treat the filters as defense in depth alongside app-level and agent-level controls. And above all, you rely on the gateway for logging and attribution, even when a filter misses. The gateway is the one place you can enforce no personal data leaves our walls and nothing dangerous comes back across the entire company at once, so it becomes the audit boundary for AI, with the caveat that it's a logged, defense-in-depth layer, not a guarantee. A gateway you can't see into is worse than no gateway, because it's a single point of failure you're flying blind on. And observability here isn't generic metrics. LLM traffic has its own signals. Log per request, the tenant and virtual key, the model and provider chosen, input and output token counts, cost in dollars, latency split into time to first token and total, cache status, exact hit, semantic hit, or miss, whether a retry or fallback fired, and the routing decision. From those you build the dashboards that run the system, cost attribution, which team, feature, or model drives spend, the report finance actually asks for. Cache hit rate, is caching paying off, and did a threshold change tank it? Per provider health and latency, which feeds the circuit breaker, and fallback and retry rates, where a rising fallback rate is an early warning a provider is degrading. The alerts that matter, cost anomalies, a spike means a runaway loop or an attack. Latency and time to first token regressions, error and fallback surges, and budget thresholds approaching. And a subtle, important one. Monitor cache hit quality, not just hit rate, because a semantic cache with a too loose threshold shows a great hit rate while quietly serving wrong answers. So a high hit rate can be a symptom of a bug, not a win. Sample and evaluate cached responses. The gateway centralizes not just traffic, but visibility, so you can attribute every dollar. Catch a degrading provider before users do, and notice when an optimization has quietly started lying to you. Streaming deserves its own beat, because it's where several earlier chapters collide, and interviewers probe it to see if you've actually built one. Most interactive LLM experiences Stream tokens as they're generated so the user sees words appear immediately, which means time to first token, not total latency, is the number users feel. The gateway must pass the stream through with minimal buffering, translating each provider's chunk format into your unified format on the fly, without adding perceptible delay. Now, the collisions. Streaming breaks clean failover. Once you've streamed the first token to the user, you can't transparently fail over to another provider mid-response. The user already saw output, so failover has to happen before first token, during connect, and once streaming starts, you're committed, which means your timeout and health decisions concentrate in that pre-first token window. Streaming complicates retries and billing. A stream that dies halfway has already produced and billed partial tokens, so just retry, double charges, and may duplicate content, so you handle partial failures explicitly. And streaming complicates caching and output safety. You can't hash a complete response you haven't finished receiving, and output data loss prevention that needs the whole answer fights against streaming it token by token, so safety-critical paths sometimes buffer, trading time to first token for a safety scan. Streaming makes time to first token the real latency metric and forces every other feature to respect a hard rule. You get exactly one shot before the first token, because after that, you can't reroute, cleanly retry, or fully scan. So failover and safety decisions live in the pre-first token window. The staff-level move is knowing you probably shouldn't hand-roll all of this. Everything we've designed, unified API, caching, routing, failover, budgets, keys, observability, is exactly what a mature ecosystem now provides. On the open-source, self-host side, LiteLLM, the popular proxy that gives you an OpenAI-compatible endpoint over 100-plus providers, and Envoy AI Gateway built on the battle-tested Envoy proxy. On the managed side, Portkey, Cloudflare AI Gateway, Kong AI Gateway, and True Foundry, which bundle routing, caching, budgets, and dashboards. So the honest answer isn't, I'd build it from scratch. It's a build versus buy judgment. Adopt an existing gateway for the standard control plane features and speed, and build custom only where you have genuinely unusual needs, a proprietary routing model, strict data residency, deep integration with internal identity or billing. But then, land the caution. A gateway is critical infrastructure that every request and every provider key flows through, so its supply chain is part of your threat model. The cautionary tale is real. A backdoor was slipped into a popular AI gateway package, lived for about 3 hours, and pulled roughly 47,000 times before it was caught. So if you adopt, pin and vet versions, scan dependencies, and treat a gateway upgrade as a privileged change, because the very centralization that makes a gateway powerful also makes a compromised one catastrophic. The rapid fire that shows range, embeddings, and non-chat traffic. The gateway shouldn't only front chat completions, route embeddings, image, audio, and re-rank calls too, since they have the same cost, reliability, and keys concerns. Batch versus interactive. Separate the paths. Interactive traffic is latency critical. And streams, batch work should use provider batch APIs, often about half the cost, and async queues, and the gateway routes by service level. Prompt management. A mature gateway versions prompts centrally, so you can update and A/B a prompt without redeploying apps, with rollback. Model A/B testing and canaries. Because the app is provider agnostic, the gateway can shadow or split traffic across models to compare cost and quality, and canary a new model on 1% first. Data residency. Route European tenants only to European region endpoints, which is a routing policy, and centralizing it is a selling point. Self-hosted fallback. For the reliability flaw and for sensitive data, keep an open model on your own GPUs as the last link in the fallback chain. And determinism for testing. Pin model versions and set temperature to 0 when you need reproducible evaluations of routing and cache behavior. Each is one crisp sentence that says, "I've operated this." The traps that sink the interview. 1. It's just a proxy that forwards requests, missing that it's a control plane for cost, reliability, and safety. 2. Calling one provider directly with no failover, the cold open outage. 3. Treating the semantic cache as a pure win, no threshold trade-off, no cross-user partitioning, no freshness, the confidently wrong trap. 4. Caching personalized or permissioned answers globally, a data breach at cache speed. 5. Rate limiting on request count, not tokens, meaningless when one request can be 200,000 tokens. 6. No budget caps, the silent runaway bill. Budgets must reject before spending. 7. Ignoring the gateway's own latency and availability, putting a fat, stateful, single-instance bottleneck on every request's hot path. 8. Provider API keys embedded in apps instead of brokered virtual keys, unrevocable and unattributable. 9. Retrying blindly, double-charging on expensive or streamed calls. 10. No observability, flying blind on a single point of failure. 11. Ignoring streaming's constraints, assuming you can fail over or fully scan midstream. 12. Hand-rolling everything and ignoring the supply chain or adopting a gateway without pinning and vetting it. Hit even a few, and the interviewer knows it's a diagram, not a design. So, an AI gateway is a control plane, not a proxy, because the moment you depend on an LLM API, you've outsourced your reliability, cost, and safety to a vendor, and the gateway is the one choke point where you take them back. Frame the requirements around what an LLM call really is. Slow, non-deterministic, metered, rate-limited, third-party, and collapse the N by M integration mess into apps to gateway to providers. Design it as a lean, stateless, horizontally scalable request lifecycle. Authenticate, budget check, cache, route, call, normalize, log. Expose one unified API, so which model becomes runtime config. Cache in 3 layers, exact match for free, provider prefix caching for up to 90% of your static context, and the semantic cache for meaning-level reuse. But respect that the semantic cache is the one thing that can confidently serve the wrong answer to the wrong user in a millisecond. So scope it, partition it by identity, and tune the threshold. Route each query to the cheapest model that answers it well. Wrap every call in timeout, retry, circuit breaker, and a fallback chain so a provider outage becomes a reroute. Meter in tokens and dollars with per-tenant budgets and hard caps. Broker secrets so real keys live in one revocable place. Enforce redaction, output data loss prevention, and audit at the gateway. Observe cost, time to first token, cache status, and provider health, and watch cache quality, not just hit rate. Respect streaming's one shot before first token rule. And build versus buy honestly, adopt a proven gateway, build only your custom edges, and vet its supply chain because it sees every key. Get that? And you can design the layer every serious AI company is building right now. Practice this exact interview with an AI interviewer that pushes back, free at crackit.io. Design the system, then go defend it. See you in the next one.